The universe does not care about our sense of scale. It operates on a level of physics so indifferent, so profound, that it forces us to rethink everything we know about stability. You think you are standing on solid ground. You aren't. You are standing on a potential. We are journeying into the invisible bubble that could rewrite the laws of existence in the blink of an eye. This isn't merely a theoretical curiosity. It is the realization that the ground beneath all of existence might already be crumbling. The physicists who first calculated its probability didn't dismiss it. They sat with it. They let it settle into their bones. And then they kept working. Because what else do you do when you discover that reality itself might have an expiration date? To understand its terrifying scale, consider this. There may be a bubble of lower energy vacuum expanding outward from some point in the universe right now, at the speed of light, erasing everything it touches not through fire or collision, but by rewriting the fundamental laws of physics themselves. Every atom it passes through simply ceases to be the kind of atom that can exist. Every star, every planet, every arrangement of matter that has ever come together in the history of the cosmos is quietly, instantly, and permanently unmade. And we would never see it coming, not for a single second. By the time we finish tonight, you will comprehend the true anatomy of this giant and how it quietly dictates not just the fate of galaxies, but the fate of reality itself. You will understand why the vacuum of space is not empty, why it has energy, why that energy may not be at its lowest possible value, and why the answer to that last question is perhaps the most consequential unknown in all of science. Before we drop into the void, take a second to subscribe. Now, let's begin. To understand the bubble, we first have to understand the ground it travels through. And that ground is not nothing. That is the first thing we must dismantle tonight, slowly and carefully, because it is the foundational misunderstanding that separates the casual observer from someone who truly feels the weight of what we are discussing. When we look at the space between stars, between galaxies, between the great filaments of the cosmic web, we are tempted to call it empty. We are tempted because our intuition was built in a world of surfaces and objects, a world where the absence of a thing means the presence of nothing. But the universe was not constructed by our intuition. It was constructed by quantum mechanics, and quantum mechanics has a very different definition of nothing. In quantum field theory, which is the most precise and exhaustively tested framework we have for understanding the fundamental nature of matter and energy, every particle we have ever observed is not a tiny ball floating through space. It is an excitation. It is a ripple. It is a local disturbance in an underlying field that permeates all of space and all of time. The electron is not a particle in the classical sense. It is a vibration in the electron field. The photon is not a discrete pellet of light. It is a ripple in the electromagnetic field. Every type of particle we know corresponds to its own field, and those fields do not go away when there are no particles in them. They are still there. They extend across the entire observable universe and beyond. They simply happen to be in their ground state, their lowest energy configuration, when no particles are present. And here is where the story begins to get strange. Even in that ground state, even when a quantum field is as calm and as quiet as it can possibly be, it is not perfectly still. It cannot be. This is not a limitation of our measurement technology. This is not an engineering problem we might one day solve. This is a hard, non-negotiable consequence of the Heisenberg uncertainty principle, one of the bedrock axioms of quantum mechanics. The uncertainty principle tells us that we cannot simultaneously know both the precise energy of a system and the precise moment in time at which it has that energy. The more precisely we pin down the time, the more uncertain the energy becomes, and vice versa. This means that at any given instant, the energy of a quantum field is not perfectly defined. It fluctuates, it shimmers, it breathes in and out of existence in tiny, momentary deviations from its average. We call these quantum fluctuations. And in the vacuum of space, they are happening everywhere, all the time, without pause, without permission, and without any observable source of energy to drive them. Pairs of virtual particles constantly flicker into existence and annihilate each other in timescales, so short that they cannot be directly detected as individual events. But their cumulative effect on the energy of the vacuum is real. It is measurable. It has been measured. This energy inherent to empty space, the energy that the vacuum possesses simply by virtue of being a quantum mechanical system, is called the zero-point energy of the vacuum, and it gives rise to what physicists call the vacuum energy density. This is a number, a measurable quantity, that describes how much energy is packed into every cubic centimeter of what we would ordinarily call empty space. Now, here is the critical bridge we need to cross, because this is where the abstract becomes dangerous. Quantum field theory, our best theory of particles and forces, predicts an enormous vacuum energy. Enormous is actually an understatement that borders on the absurd. The naive calculation, when you add up the zero-point energies of all the quantum fields we know about, gives a vacuum energy density that is somewhere between 60 and 120 orders of magnitude larger than what we actually observe. This discrepancy, known as the cosmological constant problem, is considered the worst prediction in the history of theoretical physics. It is not a small error. It is not a rounding mistake. It is a disagreement between theory and observation, so catastrophically large that it implies we are missing something fundamental, something so deep in the structure of our understanding that we have not yet conceived of the right question to ask about it. The observed vacuum energy, the one we can infer from the accelerating expansion of the universe, from the behavior of galaxies, from measurements of the cosmic microwave background, is tiny. It is almost nothing. It is a whisper compared to the roar our equations predict. And yet it is not zero. It is positive. It is real. It is there. We call it the cosmological constant, represented by the Greek letter lambda, and it is the energy of the vacuum in its current state. But here is the question that opens the door to the bubble. Is this the lowest possible energy the vacuum can have? Because in quantum mechanics, there is a crucial distinction between the lowest energy state a system has found and the lowest energy state that system could possibly occupy. These two things are not always the same. A system can be trapped in what physicists call a local minimum. It can be sitting in a valley that feels like the bottom. That is the bottom as far as anything in the immediate vicinity is concerned. But that is not the true global minimum. There is a deeper valley somewhere else in the energy landscape. And if the system ever finds a way to tunnel through the barriers separating it from that deeper state, it will fall into it, instantly and irreversibly releasing the difference in energy. We see this in chemistry. We see it in condensed matter physics. We see it in superconductors and ferromagnets and the phase transitions of ordinary water as it freezes. In each of these cases, a system exists in a higher energy metastable state until something triggers the transition to a lower energy stable state. The transition can be dramatic. It can release enormous amounts of energy, and once it has begun, it cannot be undone. The hypothesis of vacuum decay is the application of this exact logic to the vacuum of space itself. If the vacuum of our universe is not in its true ground state, if it is sitting in a metastable configuration, a false vacuum, then it is in principle capable of undergoing a phase transition to the true vacuum. The true vacuum would be a configuration of the quantum fields that has lower energy than what we currently observe. And the process by which this transition would begin is quantum tunneling. Let us sit with quantum tunneling for a moment, because it is one of the most counterintuitive and yet thoroughly confirmed phenomena in all of physics. And it is the mechanism at the heart of everything we are discussing tonight. In classical physics, a ball sitting in a valley cannot escape that valley unless it is given enough energy to climb over the surrounding hills. This is intuitive. This matches our everyday experience. You cannot roll a ball up a hill, it doesn't have the energy to climb. But quantum mechanics does not respect this intuition. In quantum mechanics, a particle described by a wave function does not have a perfectly defined position. It has a probability distribution. And if that probability distribution overlaps even slightly with the region on the other side of the barrier, there is a non-zero probability that the particle will be found there, even if it never had the energy to classically traverse the barrier. This is tunneling. It is not metaphorical. It is not an approximation. It is real, and it powers the nuclear fusion in the core of our sun, the radioactive decay of unstable nuclei, the operation of tunnel diodes in modern electronics, and the mechanism by which a scanning tunneling microscope can image individual atoms. For the vacuum of space, the relevant question is whether the quantum fields that constitute the vacuum can tunnel from their current metastable configuration into the true, lower energy vacuum state. The probability of this happening at any given point in space at any given moment is extraordinarily small, so small that it may never have happened in the entire observable universe up to this point. So small that it may not happen for an unimaginably long time in the future. But it is not zero, and if it is not zero, then it will eventually happen. And when it does, the consequences are total. Picture the energy landscape of the vacuum as a vast, rolling terrain. We currently exist in a valley. The valley is comfortable. The valley supports the physics we know, the atoms we are made of, the forces that bind them together, the chemistry that produces life, the thermodynamics that allows stars to shine. Everything we know about reality is predicated on the specific energy of this valley, on the specific values of the fundamental constants that this vacuum configuration produces. Now imagine that somewhere, separated from our valley by a thin but very tall hill, there is a much deeper valley, a truer minimum, a configuration of the quantum fields with substantially lower energy. The laws of physics in that valley would not be the laws of physics we know. The mass of the electron might be different. The strength of the electromagnetic force might be different. The fine structure constant, which governs the way atoms bind together, might be different. And in that different configuration, the chemistry of life, the stability of atoms, the coherence of molecular structures, simply does not exist, not because it was destroyed, but because the rules that allow it to exist were rewritten. At some point in space, perhaps long ago, perhaps right now, perhaps in a galaxy a billion light-years away, a quantum fluctuation occurs that is large enough to nucleate a bubble of true vacuum. In that tiny region, perhaps smaller than a proton, the quantum fields slip through the barrier and settle into the deeper valley. And in that region, for the first time in the history of the universe, the true vacuum exists. The bubble does not stay small. The transition from false vacuum to true vacuum releases energy. The difference in vacuum energy density between the two states is pumped into the wall of the expanding bubble as kinetic energy. And because the bubble wall is now carrying that energy, and because energy in the form of kinetic motion cannot be taken back without a corresponding energy expenditure, the bubble wall accelerates outward. It is not merely expanding. It is being pushed. It is being driven by the fundamental thermodynamic imperative of a system seeking its lowest energy configuration. And because nothing in the false vacuum outside the bubble can exert a greater inward force than the energy difference driving the expansion, the bubble accelerates without limit, asymptotically approaching the speed of light from the inside. For practical purposes, for any practical purposes we could ever have, the bubble wall travels at the speed of light. This means something devastating. It means the bubble is completely undetectable until the moment it arrives. Light itself, the fastest thing in the universe, the medium by which we receive all information about distant events, travels at the same speed as the bubble wall. No signal, no warning, no electromagnetic radiation of any kind can outrun the bubble wall and reach us before the bubble does. If a vacuum decay event occurred in the Andromeda Galaxy 2.5 million years ago, the bubble wall would arrive at Earth simultaneously with the first photons from that event. We would have no warning, not a microsecond, not a nanosecond. The physics of our location would simply change instantaneously with the arrival of the wall. And what happens at the wall? This is one of the most fascinating and deeply unsettling aspects of the entire phenomenon, and it is worth spending considerable time here, because the mechanics of what the bubble wall actually does to matter and energy as it passes through are deeply tied to the underlying physics of quantum field theory. When the bubble wall reaches a region of space that is currently in the false vacuum, it is carrying with it the configuration of the true vacuum. It is, in a very real sense, a domain wall, a boundary between two distinct phases of space. On one side, the false vacuum, our universe, our physics, our reality. On the other side, the true vacuum, the deeper valley, the rewritten laws. As the wall sweeps through a point in space, the quantum fields at that point are forced to rapidly transition from their false vacuum configuration to the true vacuum configuration. This is not a gradual process. It is not a slow relaxation. It is an abrupt, violent rearrangement of the fundamental fields that govern all of reality at that location. The energy released by this transition is enormous, potentially many orders of magnitude larger than the energy released by any nuclear process we know. It is dumped into the wall, further fueling its expansion. For matter caught in the transition, the consequences are not that the matter explodes or burns or is torn apart in any conventional sense. The consequences are more absolute than that. The matter simply finds that the rules governing its existence have changed. The Higgs field, which is responsible for giving elementary particles their mass, may settle at a different value in the true vacuum. If the true vacuum has a different Higgs field value, then the masses of all elementary particles are different. The mass of the electron changes. The mass of quarks changes. The binding energies of protons and neutrons change. The stability of atoms as we know them changes. In many models of vacuum decay, the true vacuum is one in which atoms cannot form at all, or in which the only stable configurations of matter are completely different from anything in our current universe. In this scenario, the proton itself is unstable. The electron does not orbit at the right radius. Chemistry does not exist, not because the chemicals were destroyed, but because the forces that allow chemical bonds to form no longer work the same way. This is the distinction that separates vacuum decay from every other cosmic catastrophe we know about. A supernova destroys matter. A black hole compresses matter to infinite density. The heat death of the universe disperses matter into cold equilibrium. But vacuum decay does not merely destroy matter. It does not compress it or scatter it. It changes the rules under which matter can exist. It removes from the universe, permanently and completely, the possibility of the kind of matter that makes up everything we have ever known. And because the bubble expands at the speed of light, and because our universe is finite in age and therefore finite in causal extent, the bubble will, if it ever nucleates, eventually encompass the entire observable universe. Every galaxy, every star, every planet that has ever formed, every molecule of water that has ever pooled in a living ocean, every atom of carbon that has ever been woven into a strand of DNA. All of it swept through the wall. All of it transitioned into a configuration that bears no resemblance to what it was a fraction of a second before. Now, we must be precise here, because precision is the difference between understanding and fear is not what we are building tonight. We are building comprehension. The precise probability of spontaneous vacuum decay depends entirely on the shape of the Higgs potential, which is the mathematical function that describes the energy of the Higgs field as it varies across different field values. Think of the Higgs potential as a landscape, just like the vacuum energy landscape we described earlier, but specifically for the Higgs field. At its current value, the Higgs field sits at what appears to be a minimum of this potential. But recent precision measurements of the mass of the Higgs boson and the mass of the top quark suggest something unsettling. When you take the measured values of these two masses and you run them through the renormalization group equations that govern how quantum field theory parameters change with energy scale, you find that the Higgs potential, when extrapolated to very high field values, very high energies, develops a second minimum, a deeper one. The potential dips below its current value at field configurations far from where we currently sit. This is not a theoretical speculation. This is a calculation performed with real, measured numbers, refined over decades of accelerator experiments, confirmed and reconfirmed with increasingly precise measurements. The central values of the Higgs boson mass and the top quark mass, as best as we can measure them today, place our universe in a region of parameter space that physicists call metastable. Not stable, not unstable, metastable. The current best estimate for the lifetime of our vacuum, if these central values are correct and if no new physics beyond the standard model intervenes to stabilize the potential, is a number so large it makes the current age of the universe look like the blink of an eye. The numbers commonly cited are on the order of 10 to the power of several hundred years, longer than the time it takes for black holes to evaporate through Hawking radiation, longer than any physical process we currently know about. So long that for all practical purposes it might as well be infinite. But it is not infinite, and the word metastable is not the same as stable. There is an important caveat that we must address carefully, and it is this. The calculation of the vacuum lifetime depends sensitively on the exact values of the Higgs boson mass and the top quark mass. The uncertainty in the top quark mass measurement, in particular, is large enough that the true value could fall in a region of parameter space that makes the vacuum completely stable, rather than merely metastable. Or it could fall in a region where the vacuum is already unstable, meaning it should have decayed long ago, but simply hasn't yet by random chance. The difference between these scenarios is physically enormous, but the difference in the measured masses that would distinguish them is only a few giga-electron volts, which is at the edge of our current measurement precision. This is one of the reasons why the precise measurement of the top quark mass at future particle colliders is considered one of the most important experimental goals in fundamental physics. We are trying to determine, with our most sophisticated instruments, whether the ground beneath all of existence is solid or whether it is a thin crust over a void. There is also the question of what physicists call high-energy nucleation. The spontaneous tunneling rate is tiny, but it is not the only mechanism by which a vacuum decay event could be triggered. High-energy collisions, like those that occurred in the very early universe during the period of cosmic inflation and reheating, could in principle provide enough energy to push the Higgs field over the barrier and into the deeper minimum. This raises the question of whether our universe survived the Big Bang and the subsequent high-energy epoch precisely because the barrier is high enough, or whether we simply got lucky, or whether the calculations predicting this kind of nucleation are wrong. Some physicists have argued that if the universe survived billions of years of cosmic ray collisions, some of which involve energies far exceeding those achievable at any particle accelerator we will ever build, then the vacuum must be stable against any reasonable nucleation mechanism. Others argue that this reasoning is flawed, that the statistics of cosmic ray collisions are not the same as the statistics of a tunneling event from a carefully prepared state, and that the survival of the universe to date tells us less about future stability than we might hope. What we can say with confidence, with the sober confidence of careful science, rather than the false confidence of popular science, is this. We do not know with certainty whether our vacuum is stable. We have strong reasons to believe it is at least very long-lived. We have no evidence of an ongoing or imminent vacuum decay event. The universe around us behaves exactly as we would expect it to if we are sitting comfortably in a metastable or stable vacuum configuration. But the theoretical possibility, grounded in our most precise and successful physical theories, is real. And the consequences, if it were to occur, would be the most complete and total event in the history of the cosmos. We should also spend time understanding what the true vacuum might actually look like, because this is where the thought experiment becomes both fascinating and philosophically vertiginous. If the Higgs field settles at a different value in the true vacuum, the masses of all elementary particles change. The electron's mass might be larger or smaller. If it is larger, Electrons orbit much closer to atomic nuclei, and the chemistry of covalent bonds, the sharing of electrons between atoms that produces every molecule in every living thing, becomes impossible or radically different. If the electron mass is smaller, electrons can barely be bound by atomic nuclei at all, and matter as we know it simply does not cohere. There is a very narrow range of electron masses that allows for the rich chemistry we know, and the true vacuum, if it exists, has no obligation to land within that range. The fine structure constant, which governs the strength of the electromagnetic interaction, and is currently approximately 1/137, might be different. This constant determines how strongly charged particles interact with light and with each other. If it were even a factor of 2 larger or smaller, the periodic table of elements as we know it would not exist. The nuclear physics that allows stars to fuse hydrogen into helium and then into heavier elements would be disrupted. Carbon, the backbone of all known biochemistry, forms through a specific nuclear resonance that depends exquisitely on the precise value of the strong nuclear force. A slightly different fine structure constant, a slightly different strong force coupling, and that resonance does not exist, and carbon does not accumulate in stellar interiors, and rocky planets do not form, and we do not exist. The true vacuum has no knowledge of this. It has no obligation to be life-permitting. It is simply a lower point on an energy landscape. And if it is lower than where we currently sit, then where we currently sit is not the bottom, and the bottom is waiting. There is something deeply important to hold on to as we sit with all of this, something that keeps this from being mere terror, and makes it instead something closer to profound scientific humility. The entire framework we have described, quantum field theory, the Higgs mechanism, the vacuum energy, the concept of the false vacuum, all of it rests on the standard model of particle physics, which, despite being the most precisely confirmed theory in the history of science, is not complete. We know it is not complete because it does not include gravity. It does not explain dark matter. It does not explain the asymmetry between matter and antimatter that allowed our universe to form. And it may not be the final word on the shape of the Higgs potential. New physics beyond the standard model, physics we have not yet discovered, could alter the Higgs potential in ways that stabilize the vacuum completely. Supersymmetry, if it exists, would modify the calculation of the top quark's contribution to the Higgs potential and could raise the energy barrier or eliminate the second minimum entirely. Extra dimensions, if they exist at some energy scale above what our colliders can probe, could change the running of the coupling constants and alter the stability analysis. We are doing our calculation with an incomplete set of ingredients, and we know it. The answer we get is the best answer we can give with what we know. It is not necessarily the truth. This is the state of the science. Not comfortable certainty, not paralyzing fear, but something in between. A clear-eyed recognition that our best theories, taken at face value with our best measurements, suggest we live in a metastable universe, that there may be a deeper ground beneath the ground we stand on, that the bubble may already exist somewhere out there, racing toward us at the speed of light, and we would have no way of knowing. And that all of this is, in a strange and humbling way, perfectly consistent with every observation we have ever made. Because if the bubble had already arrived, we would not be here to discuss it. That last thought is not a comfort, it is a tautology, but it is an honest one. To appreciate the full weight of what we have been discussing, we must travel back. Not into deep space, not yet, but into the history of human thought. Into the laboratories and the chalkboards and the quiet, fluorescent-lit offices where the idea of a false vacuum was not handed down from some cosmic authority, but was instead wrestled, painstakingly and imperfectly, out of the mathematics by a small number of people who were trying to understand something else entirely. The story of vacuum decay does not begin with a dramatic discovery. It does not begin with a telescope pointed at a strange light in the sky, or with a particle detector registering an anomalous signal. It begins, as so many of the deepest ideas in physics begin, with an equation that refused to behave. To understand where the idea came from, we have to go back to the early decades of the 20th century, when physicists were in the process of constructing quantum field theory from the ground up. The effort to merge quantum mechanics with special relativity, to create a framework that could describe particles moving at relativistic speeds while obeying the rules of quantum probability, was one of the great intellectual projects of the century. It produced, among other things, the prediction of antimatter, the calculation of the anomalous magnetic moment of the electron to 11 decimal places, and the theoretical framework for the nuclear forces that bind protons and neutrons together. But it also produced something nobody expected. It produced the vacuum, not the vacuum of classical physics, that simple absence of matter, that featureless void, but the quantum vacuum, the seething, fluctuating, energetically complex ground state of all the quantum fields that fill space. And once physicists began to take the quantum vacuum seriously as a physical entity rather than a mathematical abstraction, the question of its energy and of whether its energy was at its true minimum became unavoidable. The first person to think carefully and formally about the stability of the vacuum in the context of quantum field theory was Sidney Coleman. Coleman was a theoretical physicist at Harvard, and he was, by any measure, one of the most brilliant and original minds in the history of his field. His lectures were famous. His papers were models of clarity and depth. And in the mid-1970s, he turned his attention to a question that sounds almost philosophical, but is, in the language of quantum field theory, perfectly precise. What happens, mathematically, if a quantum field is sitting in a local minimum of its potential that is not the global minimum? What does quantum mechanics predict about the long-term fate of such a configuration? Coleman did not arrive at this question in isolation. The theoretical landscape of the 1970s was rich with new ideas about spontaneous symmetry breaking, about the way the vacuum state of a quantum field theory can itself select a preferred configuration out of a space of many possible configurations. The Higgs mechanism, which had been proposed in the mid-1960s to explain how the W and Z bosons acquire their mass, was precisely an example of this. The Higgs field sits at a non-zero value in the vacuum, a value that breaks the electroweak symmetry and gives particles their masses. The vacuum had been recognized as a dynamical object, not a passive backdrop. And Coleman wanted to understand what happened when that dynamical object was not, strictly speaking, in its most stable state. In a series of papers written in collaboration with Frank DeLucia, and building on earlier work he had done on instanton solutions in quantum field theory, Coleman developed a rigorous mathematical framework for calculating the rate at which a field in a metastable vacuum could quantum mechanically tunnel to a lower energy true vacuum. The technique he used involved a mathematical object called a bounce solution, a specific configuration of the field in imaginary time that describes the tunneling trajectory in the most probable way. The bounce solution is not a physical trajectory in the conventional sense. It is a saddle point of the action, a mathematical path through the space of field configurations that dominates the quantum mechanical tunneling amplitude. But it is extraordinarily precise, and it allows, at least in principle, a direct calculation of the decay rate per unit volume per unit time. What Coleman and DeLucia found when they applied this formalism to a realistic model of vacuum decay, including the effects of gravity, was both mathematically beautiful and physically extraordinary. The decay rate is suppressed by an exponential factor that depends on the bounce action, the action evaluated along that saddle point trajectory. For a high barrier or a small energy difference between the two vacua, the bounce action is large, and the decay rate is exponentially suppressed. The vacuum is effectively stable on any timescale of practical interest. But for a shallow barrier or a large energy difference, the bounce action can be small, and the decay rate can become significant on cosmological timescales. They also found something remarkable about what happens when the bubble forms in the presence of gravity. The inclusion of general relativity modifies the shape of the bubble wall and the dynamics of its expansion in subtle but important ways. In flat space-time, without gravity, the bubble wall expands outward from the nucleation point indefinitely, reaching the speed of light asymptotically. In curved space-time, with gravity, the picture is more complex. The energy released during the transition affects the curvature of space-time inside and outside the bubble, and the bubble's interior may itself become a new de Sitter, or anti-de Sitter space, with its own geometry, radically different from the geometry of the false vacuum it expands into. The Coleman-DeLucia paper, published in 1980, is considered a foundational text in quantum cosmology. It did not attract widespread attention immediately. Theoretical physics in 1980 was preoccupied with grand unification, with supersymmetry, with the development of string theory, and with a dozen other ideas competing for the finite attention of the community. But the paper was read, and it was cited, and it slowly accumulated the recognition it deserved as the cosmological implications of its results became clearer to a wider audience. The next major chapter in the story of vacuum decay is more recent, and it is tied directly to the discovery of the Higgs boson. For decades after Coleman and DeLucia's work, the question of whether our particular universe was actually in a metastable vacuum was, strictly speaking, unanswerable. The calculation of the Higgs potential requires knowing the mass of the Higgs boson and the mass of the top quark with precision. The top quark was discovered in 1995 at the Fermilab Tevatron, and its mass was measured to be approximately 173 giga-electron volts. But the Higgs boson remained elusive. It was the last undiscovered particle of the Standard Model, the one piece of the puzzle that had been predicted for nearly 50 years, but never directly observed. On the 4th of July, 2012, the ATLAS and CMS experiments at the Large Hadron Collider at CERN announced the discovery of the Higgs boson. Its mass was measured to be approximately 125 giga-electron volts. This was a moment of extraordinary triumph for particle physics, the culmination of decades of theoretical development and experimental ingenuity involving thousands of scientists, billions of dollars of infrastructure, and one of the most complex machines ever built by human beings. But in the weeks and months following the discovery, as physicists began to plug the measured Higgs mass into their calculations of the stability of the electroweak vacuum, something emerged that was simultaneously fascinating and deeply unsettling. The measured value of the Higgs mass, combined with the measured value of the top quark mass, placed our universe right at the boundary between stability and metastability. Not safely in the stable regime, not clearly in the unstable regime. Right on the edge. In the region, physicists came to call the metastable zone, where the electroweak vacuum is a local minimum of the Higgs potential, but not the global minimum, where the Higgs field could, in principle, tunnel to a lower energy configuration at very large field values. The papers appeared quickly. Groups at CERN, at Fermilab, at universities across Europe, Asia, and the Americas, all ran the numbers independently and arrived at essentially the same conclusion. The electroweak vacuum appears to be metastable. The estimated lifetime, depending on the precise values of the input parameters and the method of calculation, came out to something in the range of 10 to the 300 to 10 to the 600 years, numbers so astronomically large that they are essentially beyond human intuition. But they are finite, and they are grounded in real measurements of real particles detected by real instruments built and operated by real human beings. One paper in particular, by Giuseppe de Grassi and collaborators, published in 2012 in the Journal of High Energy Physics, presented the most careful and complete analysis of the Higgs potential stability at that time. It included 3-loop corrections to the running of the coupling constants, next to leading order calculations, careful treatment of the theoretical uncertainties, and a clear mapping of the parameter space showing which combinations of Higgs and top quark masses corresponded to stable, metastable, and unstable vacua. The conclusion was unambiguous within the stated uncertainties. The central values of the measured masses placed our universe in the metastable region. This result was remarkable, not only for its content, but for its precision. Here was a calculation performed with the full machinery of modern quantum field theory, using parameters measured by instruments probing energy scales far beyond anything in everyday experience, and its output was a statement about the long-term fate of the entire universe. The Large Hadron Collider, built to explore the frontiers of particle physics, had inadvertently produced the most precise measurement of cosmic mortality ever attempted. But we must be honest about the uncertainties, because honesty is what separates science from storytelling. The calculation of the Higgs potential at very high field values requires extrapolating the behavior of quantum field theory to energy scales far beyond what has been directly tested. The standard model is well confirmed, up to energies of a few tera-electron volts, the current reach of the Large Hadron Collider. But the second minimum of the Higgs potential, if it exists, occurs at field values of order 10 to the 10 giga-electron volts or higher, many orders of magnitude beyond the reach of any existing or planned accelerator. The calculation assumes that the standard model is valid all the way up to those scales, that no new physics, no undiscovered particles, no new forces or symmetries modify the running of the coupling constants in that regime. This assumption is almost certainly wrong. We know the Standard Model is incomplete. We know there must be physics beyond it, because the Standard Model cannot account for dark matter, cannot explain the baryon asymmetry, cannot incorporate gravity in a consistent quantum mechanical framework. Any of the proposed extensions of the Standard Model, any of the many varieties of supersymmetry, any of the extra-dimensional frameworks, any of the various dark matter candidates would modify the Higgs potential and could, depending on their specific parameters, either stabilize or further destabilize the vacuum. The measurement of the top quark mass is another source of significant uncertainty. The top quark is unique among the quarks in that it decays before it can form bound hadronic states, which makes its mass parameter particularly important to the stability calculation. The current best measurement of the top quark mass from combined analyses of Tevatron and LHC data is approximately 172 to 173 giga-electron volts, with an uncertainty of about half a giga-electron volt. This uncertainty is large enough that the true value of the top quark mass could place the vacuum in the stable regime rather than the metastable regime. It could equally well place it deeper into the metastable regime. We do not know. Not yet. This is why the proposal for a future lepton collider, specifically designed to measure the top quark mass and the Higgs boson self-coupling to unprecedented precision, is considered so important by the theoretical physics community. Proposals such as the International Linear Collider, the Compact Linear Collider, and the Future Circular Collider have all cited the measurement of vacuum stability parameters as one of their primary scientific motivations. We are, in a very real sense, trying to build a machine whose purpose, among many others, is to determine whether the universe will outlast its own physics. There is also the matter of how physicists think about vacuum decay in the context of the multiverse and the string theory landscape. This is a separate and more speculative story, but it is relevant here because it shapes the broader intellectual context in which vacuum decay is discussed. String theory, in its current formulation, does not predict a unique vacuum. It predicts an enormous number of possible vacuum states, estimates ranging from 10 to the power of 500 to far larger numbers, each corresponding to a different configuration of the extraspatial dimensions that string theory requires. Each of these configurations would give rise to a different set of effective low-energy physics, different particle masses, different force strengths, different vacuum energies. The collection of all these possible vacua is called the landscape, and in the landscape, transitions between different vacua, vacuum decay events of exactly the kind we have been describing, are not merely possible. They are, in some formulations, constantly occurring, driving an eternal process of bubble nucleation and expansion that populates different regions of a larger multiverse with different effective physical laws. In this picture, our universe is itself a bubble. It nucleated from some earlier, higher energy vacuum state during or before the period of cosmic inflation. The inflaton field, the field responsible for driving the exponential expansion of the early universe, can be understood in this framework as a field that was initially displaced from its true minimum and slowly rolled toward it, with the energy of that rolling driving the inflationary expansion. When the inflaton reached its minimum and inflation ended, the universe reheated and the standard model particles were produced. And the vacuum we now find ourselves in is simply the vacuum that this particular bubble happened to land in. If this picture is correct, then vacuum decay is not a catastrophe to be feared. It is a process that is happening everywhere and always. As bubbles of lower energy vacua nucleate within higher energy parent vacua across the multiverse. Our universe is the product of such a process. Our descendants, if the idea of descendants retains meaning across such scales, may exist in a bubble nucleated from ours. Cosmic history is not a linear progression, but a branching, eternal fizz of vacuum transitions, each one a universe born from the metastability of its parent. But this is speculation of a very high order. It is motivated by the mathematics of string theory and by the general framework of eternal inflation, but it is not directly testable in any conventional sense. We cannot observe other bubbles. We cannot communicate across bubble walls. We can only infer the plausibility of the framework from the internal consistency of the mathematics, and from whatever indirect imprints this process might have left on our own cosmological observables. What we can observe, what we have observed, what we continue to observe, is our own universe, our own vacuum, our own Higgs field sitting at its current value, the one that gives us our electron mass and our fine structure constant and our chemistry and our stars and our lives. And what our most careful mathematics tells us about that vacuum is that it may not be the deepest ground available, that there may be a lower valley waiting, that the barrier separating us from that valley is, by current estimates, extraordinarily high, but not infinitely so, and that the universe, given enough time, will find a way. The science of vacuum decay is, in this sense, a science of ultimate questions asked with finite tools. It is what happens when the tradition of empirical inquiry, of building instruments and measuring things and checking the measurements against theory and refining the theory and measuring again, reaches the edge of what can be directly probed. It is physics at the boundary of its own reach. And the fact that we can ask the question at all, that we can construct the formalism and make the measurements and run the calculations and produce even a probabilistic, uncertainty-laden answer about the stability of the ground beneath all of reality, is one of the most extraordinary achievements in the history of human thought. Close your eyes for a moment. Not because we are asking you to stop thinking, but because we want you to think more clearly. We want you to follow us into a place that no instrument has ever probed and no human being has ever approached. We want to take you to the wall. Let us begin far from it. Let us begin 10 billion light years from the point of nucleation. We are in the outer halo of an ancient galaxy, one of the first generation of large galaxies to form after the era of ionization, when the universe was young and bright and dense with star formation. The stars in this galaxy are old now. Many of them have completed their entire life cycles, having burned through their hydrogen in those furious early epochs when the universe was crowded and hot, having swollen into red giants and shed their outer layers and collapsed into white dwarfs that now cool imperceptibly against the cosmic background. The galaxy is quieter than it was. The era of its greatest luminosity is long past, but it is still there. Its gravity still holds its stars in their slow, orbital dances. Its interstellar medium still contains the remnants of its history, the heavy elements forged in its stellar cores and scattered by its supernovae, the carbon and oxygen and iron that mark the sites of ancient stellar deaths. In the outer halo of this galaxy, far from the dense central regions, there is a single solar system. It is unremarkable by the standards of the cosmos. A yellow dwarf star, a few rocky inner planets, a handful of gas giants farther out, a disk of icy debris at the periphery. Nothing about this system draws the eye. Nothing distinguishes it from the billions of similar systems spread across this galaxy and across the hundreds of billions of galaxies that populate the observable universe. And then, in the span of a moment so brief it has no name in any human language, something changes. It is not loud. It is not visible. There is no flash, no shock wave, no radiation that precedes it. The change is simply there, and then it is everywhere. And then everything that was is no longer. But we are not at that location. We are 10 billion light-years away. And so we watch, through the power of pure imagination and the mathematics that guides it, as the event unfolds across the immensity of cosmic time. The nucleation occurs in a volume of space smaller than a proton. In that infinitesimal region, a quantum fluctuation of extraordinary rarity has driven the Higgs field from its current metastable configuration across the energy barrier and into the deeper minimum of the true vacuum. The event is instantaneous. There is no buildup, no warning signal, no preliminary disturbance in the surrounding fields. One moment, the vacuum is as it has always been. The next moment, in a volume far too small to contain a single atom, the Higgs field has a new value, a lower one, a truer one, and the walls of the bubble begin to form. In the first instant, the bubble is smaller than any particle we know. The energy released by the transition is dumped into the bubble wall, a thin shell of field configuration that represents the boundary between the old vacuum and the new. The wall is not made of matter in any conventional sense. It is made of field. It is a region of space where the Higgs field is transitioning from its false vacuum value to its true vacuum value, a steep gradient in the field configuration that propagates outward at very nearly the speed of light from the moment of its formation. In the first second, the bubble has expanded to a radius of approximately 300,000 kilometers. This is a volume slightly larger than the Sun. Inside it, the true vacuum reigns. The physics inside the bubble are not our physics. The Higgs field has a different value. The particles that would form inside the bubble, if any were produced by the transition energy, would be a different kind of particle than anything in our experience. They would have different masses, different interaction strengths, the chemistry that makes molecules impossible, the nuclear physics that makes stable atoms impossible. Inside the bubble, reality has been rewritten from the ground up. Outside the bubble, nothing. Nothing knows. The surrounding space is exactly as it was. The stars in the galaxy where the nucleation occurred continue to burn. The photons from their surfaces continue to travel outward. The gravitational fields of every mass in the region continue to curve the surrounding space-time exactly as they have always done. There is no signal that can outrun the bubble wall. The bubble wall is not following the light. The bubble wall is the light, in the sense that both travel at the same limiting speed, and nothing faster exists in the physical universe to carry a warning ahead of the transformation. In the first year, the bubble has a radius of 1 light-year. It has already consumed whatever space lay within 1 light-year of the nucleation point. Stars, gas clouds, dust, cosmic rays, photons, neutrinos, dark matter, space-time itself, all of it swept through the wall, all of it transitioned into the true vacuum configuration. all of it rewritten. We must pause here and think carefully about what it means for space-time itself to be rewritten. Because the vacuum energy is not merely a property of matter, it is a property of the vacuum, of empty space, and the vacuum energy contributes to the energy momentum tensor that curves space-time according to general relativity. When the vacuum energy changes as the bubble expands, the curvature of space-time inside the bubble changes. The interior of the bubble is not the same universe as the exterior. It is not merely a region of the same universe with different matter content. It is a region with a different space-time geometry, evolving according to different effective physical laws. In many models of vacuum decay, the interior of the bubble is an anti-de Sitter space, a space-time with negative cosmological constant, meaning a space-time that curves inward rather than outward, that has a fundamentally different large-scale geometry than the de Sitter-like space of the expanding false vacuum exterior. The bubble wall, as seen from the interior, is not a sphere expanding outward. It is a surface retreating away in all directions as the interior space-time expands, according to its own geometry. The interior is, in a meaningful mathematical sense, a separate universe, one born from and embedded within the false vacuum, but governed by different rules. In the first 1,000 years, the bubble has a radius of 1,000 light-years. It has consumed a sphere of space larger than most molecular clouds in our galaxy. The stellar populations within that sphere, if there were any, no longer exist as stars. The regions of space they occupied are now part of the true vacuum interior, a space-time governed by physics incompatible with stellar formation, with nuclear burning, with the accumulation of matter into gravitationally bound structures as we understand them. In the first 1,000,000 years, the bubble has a radius of 1,000,000 light-years. This is a significant fraction of the distance between major galaxies in a typical group. The bubble has long since consumed its host galaxy. It has begun to encroach on the neighboring galaxies in the local group of its parent galaxy, if such a group exists. Their outer halos are already inside the true vacuum. The gas that forms their interstellar medium, the dark matter that defines their gravitational scaffolding, the stars at their peripheries, all rewritten. But the neighboring galaxies, their cores, their active star-forming regions, their planets, if any, and whatever life or complexity they may harbor, none of that knows. Not yet. The bubble wall is coming, but it is coming at the speed of light, and the light from the nucleation event is traveling at exactly the same speed. The first photons from the nucleation point, the first photons produced by the energy released in the transition, are riding the same wavefront as the bubble wall itself. Any civilization in the path of the expanding bubble, any astronomer looking at the sky with any instrument built on any physical principle we understand, would see nothing unusual in the direction of the bubble until the moment the wall arrived. And the arrival would be the end of the last moment. In the first 100,000,000 years, the bubble has a radius of 100,000,000 light-years. This is a substantial fraction of the distance to the nearest galaxy clusters. The bubble has consumed dozens of galaxies, thousands of billions of stars, uncountable planetary systems. Any life that existed in those galaxies, at any stage of development from the simplest chemistry to the most sophisticated conceivable civilization, encountered the wall. None of them saw it coming. None of them could have. None of them experience the transition because experience requires physics, and the physics of experience, the electrochemical gradients of neurons, the quantum mechanical processes of molecular biology, the thermodynamic flows that sustain complexity. All of that requires the specific configuration of physical law provided by the false vacuum we inhabit. The wall does not kill. Killing implies a victim who has been affected by a process. The wall simply removes the possibility of being, instantaneously and completely, for everything it passes through. Now we come to the most vertiginous part of the thought experiment. Let us say the nucleation occurred not 10 billion light-years away, but 1 billion light-years away. And let us say it occurred not in the distant past, but 1 billion years ago. Do the mathematics. If the bubble nucleated 1 billion years ago, 1 billion light-years from our current position, then the bubble wall has been traveling for 1 billion years at the speed of light, covering approximately 1 billion light-years of distance. The front edge of the bubble wall is, right now, reaching our location. Not tomorrow. Not in 1,000,000 years. Now. And we cannot know this. We cannot detect it. The first photon from the nucleation event, the very first light produced by that transition 1 billion years ago, is arriving at our telescopes at exactly this moment, simultaneously with the wall itself. There is no signal that preceded it. There is no anomaly in the cosmic microwave background, no unusual gamma-ray signature, no gravitational wave signal, nothing at all in the data we have collected, the photons we have counted, the neutrinos we have detected, the gravitational waves we have measured. None of it would betray the approach of the bubble. The universe would look exactly as it does, serene and ancient and full of distant light, and then the wall would arrive, and everything would be different, and nothing would be left to notice the difference. This is not a prediction. We have no reason to believe this is happening. The probability of a vacuum decay nucleation within 1 billion light-years of Earth, within the last billion years, given current estimates of the vacuum lifetime, is extraordinarily small. The numbers involved make the probability per Hubble volume per Hubble time genuinely negligible by any standard of practical concern. We are not saying this to frighten. We are saying this to convey the radical completeness of the unknowability that vacuum decay represents. Every other cosmic catastrophe we know about is, in principle, detectable in advance. A gamma-ray burst approaching our solar system would light up our detectors billions of years before it arrived. A rogue star on a collision course with our sun would be visible in our night sky for millions of years. Even a nearby supernova, one of the fastest and most violent events in the conventional cosmos, would give us years of warning from its precursor radiation before the shock wave arrived. We have instruments, we have techniques, we have strategies for detection. For vacuum decay, we have nothing. No instrument, no technique, no theoretical framework, no physical principle allows us to detect or predict a vacuum decay event before the bubble wall arrives at our location. It is the one catastrophic event in the universe that is, by the laws of physics as we understand them, perfectly and completely invisible until the moment of its completion. Let us change the scale of the thought experiment now. Let us go smaller. Let us go into the wall itself, into the boundary between the false vacuum and the true vacuum, and try to understand what happens there in the most intimate physical detail we can muster. The wall of a vacuum decay bubble is thin, In the technical language of quantum field theory, its thickness is determined by the inverse mass of the Higgs field at the field values it passes through during the transition. In practical terms, the wall is likely to be extraordinarily thin, perhaps on the order of the Planck length or the electroweak scale, far below the scale of atoms, far below the scale of nuclei, far below anything we have ever directly probed. It is, for all practical purposes, a mathematical surface, a discontinuity in the configuration of the quantum fields that has a physical extent smaller than anything we can meaningfully describe with our current physics. As the wall passes through a region of space, the Higgs field at that location changes its value from the false vacuum minimum to the true vacuum minimum. This change happens over the thickness of the wall, which passes in a time equal to the wall thickness divided by the speed of light. For a wall of electroweak thickness, this passage time is on the order of 10 to the minus 26 seconds. This is not a moment. It is not a fraction of a moment. It is a duration so brief that it makes the Planck time, the shortest meaningful interval in physics, look leisurely by comparison. During this passage, the mass of the electron at that location changes. The mass of the quarks changes. The coupling strengths between particles and fields change. The stability conditions of protons and neutrons change. Everything that was a stable, self-consistent physical system in the false vacuum finds itself, in that 10 to the minus 26 second window, in an environment where the rules have changed. There is no time for the system to adjust. There is no time for any physical process to respond. The wall simply passes through, and on the other side, the system must either be consistent with the true vacuum physics, or it ceases to be. For a hydrogen atom, for example, the passage of the wall would mean that the electron-proton system, which is stable in the false vacuum because the electromagnetic force, the electron mass, and the Bohr radius all conspire to create a stable ground state configuration, finds itself in a vacuum where those parameters are different. The ground state of hydrogen in the true vacuum, if hydrogen can exist in the true vacuum at all, might have a completely different energy, a completely different radius, a completely different set of allowed transitions. If the true vacuum is incompatible with any stable atomic structure, then the hydrogen atom, upon the passage of the wall, simply finds itself in an unstable configuration with respect to the new physics, and it decays or dissolves according to whatever processes the true vacuum physics allow. This is not a violent process in the conventional sense. There is no explosion felt from the perspective of the atom, because there is no perspective of the atom that persists beyond the passage of the wall. There is no thermal shock, no mechanical disruption, no radiation damage in any sense we could measure with our current detectors. There is only the change in the rules, and then the new rules apply, and what was is simply no longer what can be. Now let us pull back out to the largest possible scale. Let us imagine that the bubble continues to expand for not millions, but billions of years. Let us follow it out across the cosmic web, across the filaments and voids and galaxy clusters that make up the large-scale structure of the universe. In the first billion years of its expansion, the bubble encompasses a volume of space containing what might be trillions of galaxies, each with hundreds of billions of stars, each star potentially hosting planetary systems, some fraction of those planetary systems potentially harboring the conditions for complex chemistry, some fraction of those harboring life, some fraction of those harboring minds. All of it, every node in that vast and intricate web of complexity, encountering the wall without warning and without recourse. In the second billion years, the bubble is racing across the observable universe as it would appear from the nucleation point. The universe is expanding, and the expansion of space itself means that very distant regions are receding from the nucleation point at speeds that approach and even exceed the speed of light relative to the nucleation point. But this does not save them. The bubble does not travel through space in the way that a physical object does. It is the expansion of a field configuration, and the relevant quantity is the commoving speed of the bubble wall relative to the surrounding false vacuum. In any local frame of reference, the wall arrives at the speed of light. There is no region of the false vacuum that is receding fast enough from the nucleation point to outrun the bubble forever. In the long run, in the cosmological long run, if the bubble nucleates anywhere in the observable universe, it will eventually encompass everything that is not beyond the cosmological event horizon of the nucleation point. Everything within the causal future of the nucleation event will be swept through the wall. Everything outside it, the regions of the universe so far away that the expansion of space has already moved them beyond causal contact with the nucleation point. Those regions are safe in a technical sense. They will never be reached by the bubble, not because the bubble is slow, but because the universe between them is expanding faster than the bubble can cross it. But in a universe as large and as old as ours, the fraction of the observable volume that falls within the causal future of any given nucleation event is enormous. A nucleation event occurring today, anywhere within the current observable universe, would eventually sweep through a volume containing the vast majority of the matter and structure that we can currently observe. Let us sit in the stillness of that for a moment. Somewhere in the observable universe right now, quantum fluctuations are occurring in the Higgs field. They are occurring everywhere, all the time, at every point in space. The vast majority of these fluctuations are tiny, far too small to push the field over the barrier and into the true vacuum. They rise and fall in the foam of quantum uncertainty, leaving no lasting trace. But they are happening, and each one of them represents, in the language of probability, a trial, a test, a momentary query put to the universe about whether the vacuum will hold. The universe has been running this test for 13.8 billion years. Every point in space has been running the test continuously since the Big Bang, or since whatever early phase of the universe established the current vacuum configuration. The total number of quantum fluctuations that have occurred in the Higgs field across the entire observable universe over the entire age of the universe is a number that dwarfs any ordinary large number we might use in everyday scientific contexts. And yet, the universe is here. The vacuum has held. The test, run an unimaginable number of times, has come back negative every single time so far. This is either because the barrier is genuinely extraordinarily high, so high that even this enormous number of trials has not produced a single success, which is entirely consistent with the calculated vacuum lifetimes. Or it is because we are in one of the rare regions of a much larger universe where the vacuum has not yet decayed, a version of the anthropic reasoning we touched on earlier. Or it is because our understanding of the Higgs potential is incomplete, and the true potential, shaped by physics beyond the standard model, is different from what we calculate. We do not know which of these is the correct reason. We may not know for a very long time. We may never know. But we are here, and the vacuum is holding. And the bubble, if it exists somewhere in the darkness beyond our sight, is traveling. And between us and it, if it exists, there is only space and time and the speed of light that is both the fastest thing in the universe and the very thing that guarantees we will never see it coming. This is the thought experiment, not a horror story, not a prophecy, a meditation on the completeness of our cosmic vulnerability and on the extraordinary, improbable, humbling fact that we are here at all to contemplate it. To understand where the bubble is going, we must first understand where it came from. And to understand where it came from, we must go back. Not merely to the beginning of our universe, not merely to the Big Bang, but to the conditions that preceded it, to the state of the quantum fields in those first incomprehensible moments when everything that exists was compressed into a volume smaller than a grain of sand, when the temperature of the universe was so high that the forces we experience as distinct and separate today were unified into a single, undifferentiated superforce, and when the vacuum itself was something entirely different from what it is now. This is not a digression. This is the origin story of the false vacuum. Because the vacuum we inhabit today, the one whose stability we have been examining with such care, did not spring into existence fully formed at the moment of the Big Bang. It was created. It was settled into. It was the product of a phase transition that the entire universe underwent in its very earliest moments. A transition so dramatic and so fundamental that it shaped every physical law that would govern every subsequent event in the history of the cosmos. In the very first moments after the Big Bang, the universe was dominated by energy densities so extreme that our current physical theories break down entirely. The Planck epoch, the first 10 to the minus 43 seconds, is a regime where quantum gravity effects are expected to be dominant, where space-time itself is thought to be fluctuating and uncertain at the smallest scales, and where none of our current equations can be trusted to give reliable predictions. We are honest about this. The Planck epoch is, at present, beyond the reach of our theoretical tools. But as the universe expanded and cooled, moving past the Planck time and into regimes we can begin to describe mathematically, the quantum fields that permeate space began to find their equilibrium configurations. At temperatures of 10 to the 27 Kelvin, which corresponds to times of the order of 10 to the minus 36 seconds after the Big Bang, the universe is thought to have undergone a period of extraordinarily rapid exponential expansion, called cosmic inflation. The precise mechanism of inflation is still debated, but the general framework involves a scalar field, the inflaton, that was displaced from its true minimum and slowly rolling toward it. The energy of this displaced inflaton field dominated the energy density of the universe and drove the exponential expansion, doubling the size of the universe in extraordinarily rapid succession, perhaps 60 or more times in a tiny fraction of a second. What is critical for our story is what inflation did to the quantum fields, including the Higgs field and whatever other scalar fields may exist at those energy scales. During inflation, the universe was in a state very different from our current vacuum. The Higgs field may not have been at its current value. The symmetries that are broken in our current vacuum may have been unbroken at those temperatures. The electroweak symmetry, which gives us the distinction between the photon and the W and Z bosons, between electromagnetism and the weak nuclear force was restored at temperatures above approximately 10 to the 15 Kelvin. Below that temperature, the symmetry broke spontaneously. The Higgs field settled into a non-zero value, and the particles we know acquired their masses. This is the electroweak phase transition. It occurred when the universe was approximately 10 to the minus 12 seconds old. Before it, the universe was in a symmetric phase, a configuration of the quantum fields that looks very different from our current vacuum. After it, the universe was in the broken phase, the vacuum we inhabit today, with the Higgs field at its current value and the particle masses we observe. This transition is, in a deep sense, the birth of our current vacuum. The moment when the universe settled, for the first time, into the metastable configuration that has persisted for the subsequent 13.8 billion years. But here is the question that haunts the history of the vacuum. Was the electroweak phase transition a first-order or a second-order transition? This distinction matters enormously because a first-order phase transition proceeds through the nucleation of bubbles of the new phase within the old phase, just like the bubble we have been discussing all along. If the electroweak phase transition was first order, then our universe itself is, in a profound sense, the interior of a bubble. Our current vacuum is what formed inside those bubbles as they nucleated, expanded, and collided in the very early universe. The collision and merger of those electroweak bubbles produced the current uniform vacuum we inhabit. Precise calculations of the standard model electroweak phase transition, incorporating the measured value of the Higgs boson mass, indicate that in the minimal standard model without additional physics, the transition was not first order, but a smooth crossover. The transition happened gradually and continuously rather than through bubble nucleation. This has important implications for the generation of the matter-antimatter asymmetry of the universe, because the conditions required for the asymmetry to be generated require a first-order electroweak phase transition. The fact that the standard model does not produce one is one of the strong motivations for believing in physics beyond the standard model. But for our purposes tonight, the key point is this. Our vacuum was established through a phase transition in the very early universe, and it has been in its current configuration ever since. 13.8 billion years. This is the age of our current vacuum, and in that time, it has been extraordinarily stable. Not because it is the true ground state, we cannot say that with certainty, but because the barrier separating it from the true vacuum is very high, and because quantum tunneling through that barrier is an extraordinarily improbable event on any human or even astronomical timescale. But cosmic time is not human time. Cosmic time is not even astronomical time in the conventional sense. Cosmic time, in the context of vacuum stability, is a duration that makes the current age of the universe look like an infinitesimal opening act to a play of incomprehensible length. And to understand the fate of the vacuum and the fate of everything it supports, we must expand our sense of time to encompass scales that have no precedent in ordinary experience. Let us begin at the present and move forward. We are now approximately 13.8 billion years into the history of the universe. The cosmic microwave background has cooled to 2.7 Kelvin. The universe is expanding, driven by the cosmological constant, the dark energy that represents the energy density of our current vacuum. Galaxies are spreading apart from each other as the expansion of space carries them to ever greater mutual distances. The observable universe contains somewhere in the range of 2 trillion galaxies, each a vast collection of stars and gas and dark matter, each participating in the slow, grand unwinding of cosmic structure that began with the Big Bang and will not end for a very long time. Stars are still forming. In galaxies rich with molecular gas, the conditions for star formation are still being met. Giant molecular clouds collapse under gravity, fragment into smaller clumps, heat up as they contract, and ignite nuclear fusion in their cores. New stars are being born right now, at this moment, in galaxies across the observable universe. The rate of star formation has been declining since its peak about 10 billion years ago. Declining as the gas supply available for star formation is slowly depleted, but it has not stopped. Not yet. Over the next few billion years, the expansion of the universe will continue to accelerate, driven by the cosmological constant. Galaxies that are currently gravitationally bound to each other, in groups and clusters, will remain bound, their mutual gravity sufficient to resist the cosmological expansion. But galaxies that are not gravitationally bound to each other will recede from each other ever faster. The local group, containing our Milky Way and the Andromeda Galaxy and dozens of smaller companions, will remain gravitationally bound. But other galaxy clusters, already beyond our cosmological event horizon in a dynamical sense, will recede further into the distance, their light becoming increasingly redshifted, until eventually they will have receded so far and so fast that their light can no longer reach us at all. On a timescale of roughly 100 billion years, the Milky Way and Andromeda will have completed their merger, forming a single large elliptical galaxy that astronomers have already informally named Milkomeda. The star formation in this merged galaxy will have largely ceased, as the gas reservoir available for new star formation has been depleted by billions of years of stellar birth and death, and by the tidal effects of the merger itself. The galaxy will be populated primarily by old, low-mass stars, red dwarfs burning their hydrogen so slowly that they will persist for tens and hundreds of billions of years, and by the stellar remnants of higher-mass stars that have already completed their lives. White dwarfs, neutron stars, and black holes. By the time 1 trillion years have passed, 1,000 billion years, the universe will be an almost unrecognizably different place from the one we know. The cosmic microwave background will have redshifted to temperatures so cold that it is effectively indistinguishable from absolute zero. The universe will be dominated by the cosmological constant, the vacuum energy, driving an ever-accelerating expansion that has long since carried every other galaxy cluster beyond the cosmological event horizon of every other. The merged remnants of what were once great galaxy clusters will be isolated islands in an otherwise dark and expanding void, unable to communicate with each other, unable to influence each other, cut off from each other as completely as if they existed in separate universes. Within those islands, the stellar populations will be aging. The most massive stars burned out billions of years ago. The intermediate mass stars followed. Even the least massive red dwarfs, which can burn their hydrogen for 10 to 100 trillion years, will eventually exhaust their fuel and cool into cold, dark remnants called black dwarfs. The universe, on the timescale of 100 trillion years, will be populated by stellar remnants and black holes, and very little else. No nuclear burning, no light, no new stars forming. The era of stars, which began a few 100 million years after the Big Bang, and has been the dominant feature of the universe's visual landscape ever since, will be over. And through all of this, through every stage of stellar evolution, through every galaxy merger, through the formation of every black hole and the cooling of every white dwarf, through the darkening of the universe and the retreat of every galaxy cluster beyond its neighbor's cosmic horizon, the vacuum will persist. The Higgs field will sit at its current value. The fundamental constants will retain their current values. The physics of matter will remain the physics we know. And the vacuum energy, the tiny but non-zero cosmological constant that is driving the acceleration of the universe's expansion, will continue to do what it has always done, quietly pushing the cosmos apart at an ever-increasing rate. Unless, of course, the bubble finds us first. But even if it does not, the story of the vacuum is not over. Even if the vacuum is genuinely, permanently, absolutely stable, even if the second minimum of the Higgs potential is a mirage produced by our incomplete understanding of the physics at high field values, even if no bubble ever nucleates anywhere in the observable universe for any amount of time we care to consider, the universe will still evolve, and the vacuum will still play a role in that evolution. Let us move further forward in time. Let us go to the epoch of proton decay. The proton is, as far as our experiments can tell, an extraordinarily stable particle. The current experimental lower bound on its lifetime is approximately 10 to the 34 years, obtained from experiments like Super Kamiokande in Japan and its successors, which monitor enormous volumes of ultra-pure water for the rare flashes of light that would accompany a proton decay event. So far, no proton decay has been observed. But most grand unified theories, the theoretical frameworks that attempt to unify the strong, weak, and electromagnetic forces into a single unified force at very high energies, predict that protons should eventually decay, with lifetimes that range from around 10 to the 34 to 10 to the 40 years depending on the specific model. If protons decay, then all of the matter in the universe that is made of protons and neutrons, which is all ordinary matter, including the white dwarfs and neutron stars and cold planetary bodies that will be the primary repositories of ordinary matter in the far future, will eventually dissolve. Over timescales of 10 to the 35 to 10 to the 40 years, every proton in every cold remnant and every isolated island of the far future universe will undergo its final decay, releasing its rest mass energy as a shower of lighter particles, primarily positrons and pions, which will themselves decay or annihilate, releasing the energy as photons and neutrinos that spread out into the ever-expanding void. By the time 10 to the 40 years have passed, if proton decay is real, there will be no ordinary matter left in the universe. No atoms, no molecules, no cold dead stars, no planets, no dust. Nothing made of quarks. The universe will consist of black holes and the quantum fields themselves, including the vacuum, and an ever-thinning sea of photons and neutrinos spreading through an ever-expanding void. And then there are the black holes. Black holes are not eternal. Stephen Hawking showed in 1974 that black holes emit thermal radiation as a consequence of quantum effects near the event horizon, a process that slowly but inexorably causes them to lose mass, and eventually evaporate entirely. For stellar mass black holes, the Hawking evaporation time is on the order of 10 to the 67 years. For the supermassive black holes at the centers of galaxies, those containing billions of solar masses, the evaporation time is on the order of 10 to the 90 years. These are timescales that make the current age of the universe look like the very first tick of a clock that will run for an eternity. But they are finite, and black holes, given enough time, will evaporate. Their mass will be converted, through the Hawking process, into a cloud of thermal radiation, the temperature of which rises as the black hole shrinks, culminating in a final burst of high-energy particles as the last remaining mass is radiated away. And then there is nothing. No black hole, no central singularity, no trapped surface, just empty space and the quantum fields and the vacuum. By the time 10 to the 100 years have passed, even the largest black holes will have evaporated. The universe will be a cold, dark, nearly featureless expanse of expanding space, populated by nothing more substantial than a vanishingly thin sea of extremely low-energy photons and other stable particles, spread so thin across such an enormous volume that the mean free path between any two particles is larger than the current observable universe by many orders of magnitude. The average energy of these photons will be so low, so perfectly matched to the temperature of empty space in an accelerating universe, so cold and quiet and dim, that they are effectively indistinguishable from the vacuum itself. This epoch, stretching from the evaporation of the last black holes to whatever comes after, if anything, is called the dark era. It is the thermodynamic endpoint of the universe as we currently understand it. A state of maximum entropy, minimum free energy, and essentially zero capacity for any further organized physical process. Not even the decay of a single proton would be possible, because there are no more protons. Not even the slow orbit of a cold, dark remnant around a stellar companion would be possible, because there are no more remnants. There is only the void, and the fields that fill it, and the vacuum, sitting at its current energy, driving the expansion of an effectively empty universe toward a future that has no features, no structure, and no events. This is the heat death of the universe, the maximum entropy endpoint predicted by the second law of thermodynamics, applied on a cosmic scale. It is not a dramatic ending. It is not an explosion or a collapse or a cosmic catastrophe of any conventional kind. It is simply the final silence. The universe reaching the state of absolute equilibrium from which no further work can be extracted, no further order can arise, no further complexity can emerge. And in this silence, the vacuum persists. The Higgs field, still at its current value, in whatever might still be called space, still threading every point in an essentially infinite void. The vacuum energy, still non-zero, still driving the residual expansion of whatever spacetime remains. The quantum fields, still fluctuating at the Planck scale, still producing their tiny, momentary deviations from the average, still running the test, still asking the question, with every fluctuation, with every quantum breath, whether this is the moment when the barrier is breached. In the dark era, the tunneling probability per unit volume per unit time is still what it has always been. The rate has not changed. The barrier has not been eroded by the passage of time. Quantum tunneling is not a process that becomes more likely simply because time has passed. The probability of tunneling in any given second of the dark era is exactly the same as the probability of tunneling in any given second of the current era. What changes is the amount of time and the amount of volume over which the test is being run. And here is where the mathematics of probability, applied to the vast timescales of the dark era, becomes almost theological in its implications. Given a vacuum lifetime that we currently estimate at 10 to the 300 years or more, and a universe that is 10 to the 100 years old at the end of the black hole evaporation epoch, the probability that the vacuum has already decayed by that point is still extraordinarily small. We are still in the early stages of the vacuum's lifetime, from a purely probabilistic perspective. The universe, even in the dark era, is still effectively young compared to the expected lifetime of the vacuum. But extend the timescale further. Extend it to 10 to the 300 years to the nominal vacuum lifetime. At this point, the probability that a vacuum decay event has occurred somewhere in the causally accessible region of the universe is on the order of 1. Not certain, but of order 1. The universe has been running the tunneling test for long enough, over a large enough volume of space, that we would expect, statistically, to have produced approximately 1 successful tunneling event by now. 1 nucleation, 1 beginning of a bubble. And if that bubble has nucleated, it has been expanding for however long the dark era has been running. If the vacuum decays at its nominal lifetime, the bubble will have been expanding for the entire remaining age of the universe up to that point. In the dark era, the bubble's expansion is unimpeded by any structure. There is no matter to interact with, no stars to consume, no galaxies to traverse. The bubble wall sweeps through pure vacuum, through the quantum fields themselves, through the dark and empty cosmos, rewriting the physics of every cubic centimeter it passes through. In the dark era, the bubble is almost poetic in its efficiency. There is nothing to resist it, nothing to slow it, nothing to absorb even a fraction of its energy. The wall expands through the void as perfectly and as completely as a wave through still water, touching every point it reaches and changing it, irreversibly and completely, into the true vacuum. And what does the true vacuum look like in the dark era after the bubble has passed? It looks like silence, but a different silence. A silence governed by different laws. A silence in which the specific values of the quantum fields that gave rise to our universe, our chemistry, our stars, our complexity, our life, our consciousness, our questions, no longer apply. A silence that does not contain, even in principle, the possibility of the structures that made us possible. The true vacuum in the dark era is not an ending. It is a transformation. The universe does not cease to exist when the bubble passes through it. Space-time continues. The quantum fields continue. The laws of physics, whatever they may be in the true vacuum, continue to operate. But they operate in a regime so different from our own that the word continuation feels generous. It is not our universe anymore. It is something else. Something that perhaps has its own physics, its own dynamics, perhaps even its own forms of complexity, utterly alien to anything we could recognize or name. We do not know. We cannot know. Our physics ends at the bubble wall. But let us consider one more possibility, one more layer of the cosmic evolution of the vacuum, because the story does not necessarily end even here. There are theorists who have explored what happens in a universe that has undergone vacuum decay and settled into the true vacuum. The true vacuum, in many models, has a large and negative vacuum energy density, an anti-de Sitter configuration. A universe with a large negative cosmological constant does not expand indefinitely. It undergoes a recollapse, a big crunch, a reversal of the initial expansion that brings all of the universe's matter and energy back together into a region of extreme density. In the context of the true vacuum bubble, this recollapse may happen internally, within the bubble itself, on a timescale set by the energy difference between the false and true vacua. If the energy difference is large, the recollapse happens quickly. The interior of the bubble, born in the transition from false to true vacuum, expands for a while according to its own internal geometry, and then reverses, collapsing inward under the influence of the large negative cosmological constant. Everything inside the bubble, everything that was rewritten by the passage of the wall, is then compressed back into a singularity. Not our singularity, not the Big Bang from which we emerged, but a new singularity, governed by the physics of the true vacuum, carrying within it the information of every system the bubble wall passed through, encoded in whatever form the true vacuum physics allows. And from that singularity, what then? We do not know. Our physics cannot follow us past a singularity. The equations of general relativity break down at infinite density, and quantum gravity, which might resolve the singularity, is a theory we do not yet have. But theorists have speculated, and some of the speculations are extraordinary. If the recollapse and subsequent singularity lead to a new phase of expansion, a new Big Bang governed by the physics of the true vacuum, then the bubble is not just an ending, it is a beginning. The decay of the false vacuum is not a cosmic death, but a cosmic birth, the nucleation of a new universe within the shell of the old one, carrying its own initial conditions, its own inflation, its own reheating, its own matter and radiation, its own large-scale structure, and perhaps its own physical constants, constrained by the true vacuum physics, but possibly still rich enough to support new forms of complexity we cannot imagine. This possibility, deeply speculative and far beyond the reach of current observational cosmology, is nevertheless a logical consequence of taking quantum cosmology seriously. If bubble nucleation is a real process, and we have strong theoretical reasons to believe it is, then the universe we inhabit may be the product of a bubble nucleation from a parent vacuum. And any bubble that nucleates within our universe may itself become a parent vacuum for yet another generation of cosmic offspring. The vacuum in this vision is not merely a background. It is a creative medium. The transitions between vacua are not catastrophes, but generative events. The universe exploring its own landscape of possible physical layers, sampling different configurations across an enormous cosmic time. Each configuration a universe unto itself. Each universe potentially rich enough to develop its own story, its own stars, its own complexity, its own moments of consciousness looking up at a night sky and wondering what lies beyond. And the bubble, the invisible wall that we have spent this entire journey contemplating, is the mechanism of that creativity. It is the universe's way of finding lower ground, the universe's way of exploring the landscape, the universe's way of not being finished. We are inside one of these explorations right now. We are inside a bubble that nucleated from some earlier vacuum state, in some earlier phase of cosmic history that we cannot directly observe. The physics of our bubble, the specific values of our Higgs mass, our fine structure constant, our cosmological constant, our proton mass, all of it is the physics of our particular bubble, the result of the specific nucleation event that produced our universe. It is not the only possible physics. It is our physics. And it has been, as far as we can tell, extraordinarily fortunate physics. Physics that allows stars. Physics that allows carbon. Physics that allows molecules. Physics that allows minds. The bubble that might one day sweep through our universe and produce a new nucleation is the next step in this process. Not an ending, from the perspective of the cosmos as a whole, though it is an absolute ending for everything within our false vacuum. A transition, a step to lower ground, a new configuration of the fields, a new set of physical laws, a new bubble carrying within it whatever that deeper valley permits, expanding outward into whatever remains of the space-time it was born in. This is the future of the vacuum. Not merely stability or decay, but participation in an ongoing cosmic process of exploration and transition that stretches across timescales so vast they have no name in any human language, across energy landscapes of such complexity that no single mind could hold them whole, across a multiverse of such richness that the word universe itself becomes inadequate to describe what it contains. We are here, in our bubble, in our valley, in our particular moment of cosmic time, watching the stars and building our instruments and asking our questions. And the vacuum beneath us holds. For now, it holds. Come back now. Come back slowly. Come back to the room you're in. Come back to the weight of the surface beneath you, the particular temperature of the air around you, the faint sounds of whatever world exists just beyond the wall of wherever you're resting tonight. Come back to the specific, irreplaceable, unrepeatable fact of your own existence in this moment, in this place, in this universe, in this vacuum. You're made of atoms. We know this. We have known it for a long time. The carbon in your body was forged in the core of a star that died before our sun was born. The oxygen in your lungs was assembled in the nuclear furnaces of massive stars that burned and exploded across billions of years before the solar system formed. The iron in your blood was produced by a supernova, by the catastrophic collapse of a stellar core so massive that it could not hold itself up, so dense that it bounced and exploded and scattered its interior across the galaxy. You are the product of billions of years of cosmic chemistry, of stellar evolution, of planetary formation, of biological evolution, of the specific and extraordinarily improbable sequence of events that produced this planet, this biosphere, this species, this individual, this moment. All of that, every step of that extraordinary chain, every supernova, and every molecular cloud, and every primordial ocean, and every generation of living things. All of it was possible because of the vacuum. Because the Higgs field settled 13.8 billion years ago into its current value. Because the masses of the electron and the quarks and the bosons came out the way they did. Because the fine structure constant is what it is. Because the strength of the nuclear forces allows carbon to accumulate in stellar interiors and be scattered into space when those stars die. Because the vacuum energy is small enough to allow galaxies and stars and planets to form, before the universe expands too fast for structure to coalesce. Because the ground, the quantum mechanical ground of all of reality, has held. We have spent this journey examining the possibility that the ground might not hold forever, that there is, perhaps, a deeper valley waiting beneath the one we stand in, that the bubble might, at any moment, or might never, or might have already, somewhere distant, begun its silent and inexorable expansion toward everything we know. We have examined this possibility not to frighten, but to illuminate, because the depth of our vulnerability and the depth of our wonder are, it turns out, the same depth. You cannot fully appreciate the extraordinary improbability of your existence without understanding how narrow the conditions for that existence truly are. The vacuum is not nothing. We established this at the very beginning, and it bears returning to now, at the end, because it is the central truth that everything else rests upon. The vacuum is the most fundamental physical entity in the universe. It is not the absence of things. It is the substrate from which all things emerge and to which all things return. The particles we observe are ripples in the vacuum's fields. The forces we measure are interactions mediated by the vacuum's field quanta. The constants of nature, the numbers that appear in the equations of physics and determine the structure of everything from atoms to galaxy clusters, are properties of the vacuum, not arbitrary labels we have attached to the universe, but genuine features of the specific vacuum configuration we inhabit. When we talk about the possibility of vacuum decay, we are talking about the possibility of the most fundamental change imaginable. Not a change in the matter within the universe, not a change in the distribution of energy, not a change in the large-scale geometry of space-time, at least not primarily. A change in the vacuum itself, a change in the substrate, a change in the rules from which all other rules are derived. And the profundity of that possibility, the sheer ontological weight of what it would mean for the ground of reality to undergo a phase transition to a lower state, that profundity is, we think, worth sitting with for a long time. Because here is what it means for us, tonight, in this room, in this moment. It means that the physical laws we experience as eternal and unchanging, gravity pulling us toward the center of the earth, electromagnetism binding our molecules together, the strong force holding the nuclei of our atoms intact, none of these are properties of the universe in any absolute sense. They are properties of our vacuum. They are the specific physical consequences of the specific value of the Higgs field in our particular region of space-time, in our particular phase of cosmic history. They feel eternal because we have never experienced anything else. They feel fundamental because they are the deepest layer of reality we can probe with our instruments. But they are, in principle, contingent. They are one answer, among possibly many, to the question of how quantum fields can arrange themselves at their lowest available energy. This is not a nihilistic observation. It is not a reason to feel that nothing matters, that the laws of physics are arbitrary, that meaning is impossible in a universe whose foundations might be provisional. It is, if anything, the opposite. The fact that the laws of physics are what they are, the fact that this particular vacuum configuration, with its particular Higgs field value, and its particular coupling constants, and its particular vacuum energy density, happens to be one that supports the existence of atoms and molecules and stars and planets and living things and thinking things. That fact is one of the most extraordinary and humbling realizations in the history of human thought. We did not choose this vacuum. We did not design these laws. We did not set the fine structure constant or the electron mass or the cosmological constant to values that would allow our existence. These values were determined by the physics of the nucleation event that produced our universe, by whatever process in whatever parent vacuum gave rise to the bubble we inhabit. And yet, here we are, minds inside this bubble, made of the matter this bubble allows, looking out at the stars this bubble produced, asking questions that this bubble's physics makes possible. The improbability of this is staggering. If you were to randomly select a vacuum configuration from the landscape of all possible vacua, predicted by string theory, the overwhelming majority of those configurations would not support anything like the complexity we observe. Most would have vacuum energies either so large and positive that the universe would expand too fast for structure to form, or so large and negative that the universe would recollapse in a fraction of a second. Most would have Higgs field values that produce particle masses incompatible with stable chemistry. Most would have coupling constants that prevent stars from burning long enough to produce heavy elements. The fraction of the landscape that is life-permitting, by any reasonable definition of life, is extraordinarily small. And yet, here we are, in a life-permitting bubble, in a universe that has gone on long enough and been structured carefully enough to produce, after billions of years of stellar evolution and planetary chemistry and biological evolution, minds capable of discovering quantum field theory and the Higgs mechanism and the concept of the false vacuum and the possibility of their own cosmic contingency. There is something in this that goes beyond physics, not beyond science, but beyond the purely technical content of the equations. There is something in the fact that the universe has produced, within itself, entities capable of understanding the conditions for their own existence, entities that can trace the chain of physical causation from the nucleation of their vacuum, all the way back to the phase transition that set their physical constants, all the way forward to the dark era and the eventual evaporation of the last black hole. That is, in some sense, the universe achieving a kind of self-knowledge. We are the universe looking at itself. We are the vacuum examining its own stability. We are the Higgs field, through the extraordinary long detour of stellar and biological evolution, constructing instruments and equations to measure its own mass and ask whether it is sitting in the deepest valley available to it. This is not mysticism. This is a straightforward description of what has actually happened. The quantum fields that permeate the vacuum of space are the same quantum fields that, through the production of atoms and stars and planets and living things, have produced the scientists who measure them. There is a direct physical chain of causation, unbroken and entirely material, from the value of the Higgs field to the existence of the people who discovered the Higgs boson. The universe is, in a very real and non-metaphorical sense, aware of itself, through us. And that self-awareness includes the awareness of our own potential impermanence. We know that we might be living in a metastable vacuum. We know that there might be a lower valley waiting. We know that the bubble, if it ever forms, is undetectable and unstoppable. We carry this knowledge not as a weight, but as a companion. It walks with us through our science, through our measurements, through our attempts to understand the deepest structure of reality. And it does not paralyze us. It cannot paralyze us. because the improbability that gave us the vacuum we inhabit, the extraordinary contingency of our physical constants, the vanishingly small slice of the landscape we happen to occupy. That improbability is also, at the same time, the improbability of our existence. To be disturbed by the contingency of the vacuum is to be disturbed by the same contingency that produced you. And you are here, undeniably, irreducibly, extraordinarily here. The bubble may be out there in the darkness, expanding at the speed of light, carrying within its wall the transformation of everything it touches. It may have nucleated 1 billion years ago, or 1 billion years ago, or it may nucleate 1 billion years from now, or 1 billion years from now, or never. We do not know. We cannot know. And this unknowability, rather than being a failure of science, is itself one of the deepest findings of science. It tells us something true and important about the nature of the universe we inhabit. That it is fundamentally probabilistic at its deepest level. That even the ground of reality is subject to quantum uncertainty. That the most stable-seeming features of the cosmos are, at the quantum level, always subject to the whisper of possibility, the non-zero probability of transition to something different, something lower, something truer. We have instruments on the ground and in orbit right now that are measuring the mass of the Higgs boson and the top quark with increasing precision, trying to narrow the uncertainty in the stability calculation. Future colliders, if they are built, will sharpen these measurements further, perhaps to the point where we can say with genuine confidence whether our vacuum is stable or metastable. That effort, that centuries-long project of building bigger and more sensitive instruments to probe the nature of the Higgs field and the structure of the vacuum, is one of the most quietly profound undertakings in the history of our species. We are trying to determine the stability of the ground beneath all of existence. We are trying to read the warranty on reality. And whether the answer turns out to be stable or metastable with an effectively infinite lifetime, or metastable with a more dramatic prognosis, the act of asking the question is itself something worth pausing to appreciate. Because the question could not be asked from inside a proton. It could not be asked from inside a star. It could not be asked from inside a black hole. It can only be asked from inside a mind, a physical system of extraordinary complexity, built from the specific atoms that this specific vacuum makes possible, organized by the specific chemistry that this specific vacuum allows, sustained by the specific thermodynamics that this specific vacuum supports. We are asking the question, that is not nothing. That is, in a universe that has been mostly dark and cold and structureless for the overwhelming majority of its existence, something close to a miracle, not a supernatural miracle, a natural one, a miracle of physics, of chemistry, of evolution, of time, a miracle whose underlying mechanism we are slowly, painstakingly, beautifully beginning to understand. So rest now. Rest in the knowledge that the vacuum is holding, that the Higgs field is at its current value, as it has been for 13.8 billion years, as it will almost certainly be for an unimaginably long time to come, that the atoms in your body are stable, that the electromagnetic force binding your molecules is exactly what it has always been, that the fine structure constant is still 1/137, that the ground for now is solid. Rest in the knowledge that you are, in the most literal physical sense, a temporary but real manifestation of this vacuum's potential for complexity. That the same quantum fields that permeate the void also permeate you. That the zero-point energy of the vacuum, that fundamental restlessness of the quantum ground state, is the same restlessness that moves electrons through the neurons of your brain and produces the thoughts you are having right now. You are not separate from the vacuum. You are an expression of it, a particularly organized, particularly improbable, particularly self-aware expression of the fields that fill all of space and all of time. The universe is 13.8 billion years old. You're here for a cosmically brief moment within that vast expanse. The vacuum has been here since the electroweak phase transition, since the first trillionth of a second after the Big Bang. And it may be here for an incomprehensibly longer time still. But it will not always be here in its current form. Nothing is eternal. Not stars, not black holes, not the vacuum itself. Everything in the cosmos is a temporary configuration of energy, a metastable arrangement that will eventually find a lower state, whether through physics we understand, or through physics we are still reaching toward. And in that context, the brief, fragile, luminous window of ordered complexity that we call life, that we call thought, that we call wonder, is not diminished by its impermanence. It is made more vivid by it, more precious, more worth attending to. The bubble, if it comes, will not find us afraid. It will find us curious. It will find us still building instruments, still sharpening our measurements, still asking whether the valley we inhabit is the deepest one available, still looking up at a night sky full of ancient light and wondering what it all means and how it all works and whether the ground beneath it is as solid as it feels. It will find us, as it has always found us, doing the most human thing imaginable, trying to understand. Tonight we looked at the invisible bubble that could delete the universe. We found not a monster, but a mirror, a reflection of our own contingency, our own improbability, our own extraordinary good fortune to be here at all in this particular bubble, in this particular valley, with these particular laws, at this particular moment in the long and mostly dark history of a universe that, for a brief and shining interval, became aware of itself. Sleep well. The vacuum is holding.